let's move on to our next potential that we're going to solve, which is the simple harmonic oscillator. And along the way, we're going to talk about commutators, and we're going to discuss the algebraic method of finding the energy eigenfunctions for this particular potential. Now, this potential is just the spring potential that you would have used in first-year physics. So traditionally, we write this 1/2 kx squared. And so if, for instance, we had some energy here, classically, this would be our turning points where the potential energy or the kinetic energy would be 0 and the potential energy would be maximum. And if you were to sort of let your object go, it would just sort of bounce in between these 2 points here. Now, we traditionally in quantum mechanics write it this way. This will be a little bit of a better way for us to write it. And all that does is using this idea of our angular frequency. So each harmonic oscillator system, each spring-like system, all right, is going to have some angular frequency, which is the k constant divided by m. So if you plug in for k, we get this here. So it looks a little bit different from first year, but it's really just the same thing. Now, you may wonder why are physics types so interested in spring systems? Well, it's not necessarily a spring itself, but it's just that any system can be approximated, or almost any system can be approximated as a spring. So let's say we have some potential energy, some sort of complicated function, I don't know, that looks like this, all right? And if we take some point, and we'll call this point x0, so when this is at some sort of a minimum, all right, what we can do is we can look at, so for this particular function, so this is v of x, but we'll sort of, here's our law, the Taylor series expansion for some function. All right, and this Taylor series is basically a combination of the functions, so the function at that particular point, and then plus the first derivative of that function at a particular point times x minus x naught, and then the second derivative, and so on and so forth. And so whenever we're at a minimum like that, okay, so at this point here, the slope of this is 0. So this particular potential function, the slope at that x sub 0 is equal to 0. And so if I was to approximate this with a Taylor expansion, this term goes to 0. And so my expansion of that would be the first term, which is just a constant, plus the second derivative with some value plugged in divided by 2 times the distance away from x sub 0 squared. All right, and so if you write this out for our particular potential, so it'd be some constant, we'll call it some v0 squared, and then some k constant divided by 2, and then this is basically what we would call something like delta x. Okay, so again, delta x is the distance away from this point here. And so what this says is for really small oscillations, okay, oscillations where you can forget the higher derivative terms, okay, x cubed, x to the 4, so on and so forth, any minimum type function like this, okay, can be approximated by a harmonic oscillator. So that's why one of the reasons they're so interesting to us. And so the takeaway message here is that virtually any oscillatory motion is simple harmonic if the amplitude of it is very small. And you've seen this in first-year physics, for example, for a pendulum. Okay, the oscillatory motion of a pendulum is can be approximated by simple harmonic motion for very small amplitudes. And so just some real-life examples, there's a whole slew of them that basically act very similar to harmonic oscillators. Okay, atoms organized in a solid act like basically they're surrounded by a bunch of springs, okay, vibrating back and forth, molecular vibrations. In molecules, wave oscillations. And then quantum field theory, which is relativistic quantum mechanics, is really based on this idea of harmonic oscillators. So it becomes very important when you get to that. So there's a lot of applications. So it's not just springs. It's more that there's many things in nature that can be approximated by a spring-style force. And so for us, now what we're going to do is we're going to take this potential, all right, and try to solve our time-independent Schrodinger equation. Okay, so we're going to try to solve our eigenvalue equation for this particular potential. So here's again our potential, And so we're going to try to go through and find our energy eigenfunctions and the energy eigenvalues for this system. So we've talked a lot about this concept. We've only really done one example so far, which is the infinite square well. Now the book, and most books actually, have two methods to solve this. There's the algebraic, which is the one we'll talk about, and then the analytic, which I sort of call more of a brute force. And so I didn't put that down as one of the readings. You're free to read it. It uses the method of Frobenius, which is, of course, everyone's favorite method. But again, it shows you how to actually solve an equation like this by brute force. We're going to show a way that sort of solves it using a trick, and it's a trick that can be useful to us. It will be useful to us later on in quantum mechanics and in physics in general, so it's a good trick to learn. All right, so this trick revolves around writing this Hamiltonian, writing this equation in a different format. And so what we're going to do here is we're going to keep this to be e times the wave function. And then over here, we're going to kind of break this down. All right. And basically, this part here, okay, the negative h bar squared d squared over dx squared over 2m. This part here, the negative h squared, second derivative of x, that is our momentum operator twice. And so that is equal to the momentum operator squared. And so you can just replace all that stuff with a p squared. Okay, and then the book goes ahead and pulls out the 1 over 2m. And then if you pull out the 1 over 2m, what you do is you leave this here with an m omega x squared. And so the reason they do this is because then, if you look at this, this is something that at least looks like something you could factor out rather easily. Okay, and so the Hamiltonian is written this way right here, and this leads us to this algebraic method. And so the first thing we want to do is talk about what's called a commutator. So in math, most things you've probably dealt with commute with each other. And by commuting, we mean here. So we're going to define something called the commutator, and it's the commutator of a comma b. And whatever that is, you take AB minus BA. Now, for most things, okay, just numbers and constants, that's 0. But we're going to find for operators, okay, that we're using in quantum mechanics, this is not always 0. And so, for example, the commutator of x comma p equals I h bar. And so let's go through, first of all, and sort of show how to calculate this. Okay, so x comma p. Right, so for us that would be xp minus px. Now the best way to go about thinking about this is to take this and multiply it by some function. Okay, so I'm going to say x comma p times some function, which of course is going to equal xp minus px times some function. So it's just some function of x. And so I'm going to write this out. Now of course my operator for p is h bar over I dx, and so I'll plug that in. And then over here it's negative h bar over I d dx x. Okay, so now here's where the problem comes in, is that here I'm taking this derivative and then multiplying it by x. Here the x comes first. Well, this derivative is going to act on this x and have some problems. And so if we distribute this around, I get x h bar over I d by dx times f. So that's just the derivative of f. And then I got negative h bar over I. And so here's, again, where our problem comes up. I have this derivative is going to be times x and times f. And of course, due to a product rule, that's going to lead us to 2 terms. And so I think one thing I'll do is I'll just pull h bar over I out of everything. And so then here I have x times df dx. Now with this term, after I do the 2 derivatives, I'll have negative f. That's from taking the derivative of x. All right, and then d by dx of the f, I'll have negative x times df dx. And then you'll see that basically this term and this term cancel out. And so I'm led to h bar over I times negative f. All right, and then what I can do is I can just sort of say that, okay, so basically everything that's times that f will then be what my commutator is equal to. So my commutator equals negative h bar over I. So whenever you're calculating commutators, the best way to do it is to say, okay, my commutator x comma p, and then times it by some function, go through and do all your stuff, and at the end here you come out with this times the function. So this is what my commutator is equal to, and of course negative h bar over I, that's just equal to I over h bar, right? And just to double check, if I take this and if I multiply I on the top and the bottom, so multiply it by 1, I got a negative 1 on the bottom, which cancels with that, and I'm left over with I h bar. So now what I'd like you to do is calculate the opposite. So we just calculated x comma p, so go through and calculate p comma x, and we'll talk about this in a little bit. Okay, so the question is p comma x equal to the same thing as x comma p is? And well, hopefully you can see now, you can actually go through and do this like we did the last example, but you can also just show yourself that, you know, x comma p is equal to xp minus px, and of course p comma x is equal to px minus xp, and so they're just the inverse of each other, and so this would be no, and so the way that this works is if you actually go through and calculate this, it would be p comma x is equal to negative I h bar. Okay, and just important to note that, you know, what this means is that the operators x and p that we have, they don't commute. Okay, so if you have something like this turn up in your algebra, xp minus px, you can't call that 0. Another thing that I'll really note real quick is that, you know, Griffiths is getting rid of the hats when he talks about operators, and so I'll probably do the same. Now, this new way to write the Hamiltonian leads us to this definition that we call a plus and a minus, which we're eventually going to call the raising and lowering operators. And let's show exactly where this definition arises from. And so let's just take a plus times a minus, and the book does this too. And so my second step, I'll just combine these, get rid of the square root, and then I have these terms. And so I can write out 4 terms, a, b, c, and d. So if I write this out, this is the term a, c. This one here, I believe, is term, let's see, this is a times d. This one here is b times c, and then this one here is b times d. Right, so you can go through there and write those out, and so you get this stuff here. Now, there's some constants and there's some operators. You got to be very careful about the operators. And so, first of all, in this term, negative I squared is just 1, so I get p squared out of there. I keep this the same, and I sort of write these. I basically pull all the constants out, which are the same, I m omega, and then it's times xp. And so what this is actually equal to is this is actually equal to I m omega, if you look at it, the commutator of x comma p. And this is where this whole definition comes from. Let's just pretend for a second that x and p did commute. These two terms would go to 0, and you would just be led to something that looks very similar to the Hamiltonian. And so this a plus and this a minus come from this sort of imaginary idea that if these things did commute, these would be how you would factor out the Hamiltonian. Okay, and so Dirac was the first person to think about this, and he thought, well, even though they don't actually factor to make, you know, the Hamiltonian, maybe they're useful to us. And so this middle term here is I m omega x comma p. All right, and let's just look at this real quick. So again, this middle term I m omega x comma p, well, we know that commutator is equal to I h bar. And so I plug that in, I h bar, and so I go through a little bit. So here I times I gives me a negative, and I'm almost there. And now I start grouping terms together. So the one thing I do is I multiply both sides by h bar omega. And so it leaves me an h bar omega over here, and then when I multiply by h bar omega over here, I cancel out that one and that one. And so I get this terms here, and I can start pulling things out, and here, this guy is just my Hamiltonian. Okay, so this piece is just my Hamiltonian, and then this piece, once I sort of go through and factor out some things, is going to come out to be something interesting to me. And so here we got h bar omega, a plus, a minus. Again, this thing here turns out to be our Hamiltonian. So I write that as h, and then this thing here, the m's will cancel. It turns out to be negative 1/2 h bar omega. And so I can rewrite this way here. And so this is a way to write out the Hamiltonian. Okay, so the Hamiltonian it's close to A plus times A minus, but because those two terms don't commute, you get this little extra 1/2 piece here. Now I also could have done this, and I think the book does this calculation by multiplying A minus times A plus. But this gives us two definitions of our Hamiltonian, and we're going to find that by writing our Hamiltonian this way, okay, we can actually solve this system much easier than going through and doing the more brute force method. Okay. All right, so here's how this new definition can work. And these operators, the A plus and the A minus, are going to be called ladder operators. Now let's just assume, like we can, that there are functions that if I apply h times psi n, I get En times psi n. Again, this is our whole goal, to find the energy eigenfunctions and to find our eigenvalues, maybe energy eigenvalues. All right, so that's our whole goal. So let's assume that they exist. Well, if they exist, let's go through and do this. Okay, I'm going to apply my Hamiltonian to the state A plus times psi n. Okay, I'm going to see what that does. And so I'm going to apply this new special form of the Hamiltonian. You can do this with either of the two versions we came out with. I'm just going to do it with this one right here. So it's h bar omega A plus A minus plus 1/2. And again, I'm applying it on this right here. So I'm not applying it on an actual energy eigenvalue, but A plus times an energy eigenfunction. I'm applying A plus times the energy eigenfunction. And so let's just go through and do this a little bit. So the first step, what I do is I move the h bar omega into here. And then what I do is I take the A plus and sort of move it back into these sort of functions here. Okay, so I distribute it into these two pieces here. So there's an A plus here and an A plus. So now you have three of these operators acting together. And then I sort of drop down these two brackets here. Okay, write out A minus A plus and then 1/2. And so I pull out the h bar omega from both of these, and I pull out the first h plus there, and then the only h plus a plus over here. So it's h bar omega times a plus. And so I sort of I pulled out this piece here, and I sort of pulled out everything from here except for the 1/2. All right, we're going to see in a second why I do this. Now here's another question. So now I can take my definitions of the Hamiltonians and express it out in sort of a special way here. I can say A plus A minus equals this, and then A minus A plus equals this. And so we actually went through and calculated this one here, but you could also go through and calculate this one here. So if that's true, what is the commutator of A plus A minus? So think about this, and then we'll talk about it in a little bit. All right, so this is another commutator style problem. And so if I look here, this would give me A plus A minus minus A minus A plus. And if I plug in my two terms, and so here's this one term, and then here's the other term. And so hopefully you can see that when you do this, the first part will cancel out. So I have, Hamiltonian over h bar omega minus 1/2 minus Hamiltonian over h bar omega plus 1/2. And so the Hamiltonian parts cancel. The two 1/2s add up to be -1. And so I can write here A plus A minus minus A minus A plus equals -1. And so that's my commutative relationship. So hopefully that's what you got, -1. Now also, I can write that, if we get that, I know that A minus A plus is equal to 1. And so here's what I'm going to do. So A minus A plus minus A plus A minus equals 1. And so what that leads me to is this relationship here. A minus A plus is equal to 1 plus A plus A minus. And I can use this in the problem that we just had. So we just isolated A minus A plus, and so I can replace it with 1 plus A minus. All right, so here's A minus A plus, and so again I replace it with this here, and that's just from my commutation relationships. Okay, so I replaced that there, and then now what I do is I bring in the h bar omega. So that's something that always commutes with stuff. It's just a constant, so I can move it around in these commutator or with these operators, no big deal. So I get h bar omega A plus A minus plus h bar omega plus h bar omega over 2. And now we just remember that our definition of the Hamiltonian is A plus A minus plus 1/2 h bar omega. And so if you look here, this piece and this piece is my Hamiltonian. Okay, and so I can rewrite that like this right here, basically. And so as an intermediate step, maybe what would be nice is to sort of go like this, is to say, okay, so this piece here, I would have it as, well, no, that's fine. So the Hamiltonian, these two pieces come together to be the Hamiltonian, and then left over is this h bar omega. Okay, and so this is going to be really important. So I'll definitely stop and just go back if you got a little bit mixed up on this. It is pretty tricky, so I'm trying to go through all the steps here. Okay, so we're almost there. So we have this right here, and the thing is we know that h times this gives us En times psi n. So again, if we assume that that's one of our energy eigenfunctions, then now we have this written here. We get En plus h bar times that. And then, now that this is an operator, but these things are all constants, I can sort of slide it back in here because it commutes. All right, an operator will commute with constants over to here. And so we have this equation that says the Hamiltonian times whatever this thing, h plus psi n, equals En plus h bar, a plus psi n. And we can go through and do that. And basically what that's telling us is this operator, a plus, okay, if I operate it on one of the energy eigenfunctions, it gives me a new energy eigenfunction that is equal, or that is an energy eigenfunction that has the energy of that energy I started with plus h bar omega. So what it's done is it's raised us to the next higher level of energy. And this is the trick we're going to use to solve for these energy eigenfunctions. Once we solve one of them, we'll be able to solve for them all by raising each one to a higher level. Yeah, so again, let's just walk through this real quick. So we got these operators, a plus and a minus, and we got them by essentially sort of factoring the Hamiltonian. With these operators, we found new ways to write the Hamiltonian, and we used one of them, but both of them will work. And then we developed equations like this. So we did this one here, but you can also do this one over here. And so these operators, a plus and a minus, become known as the raising operator. This is the raising operator, and this is the lowering operator. And basically, if you act them on one of the energy eigenfunctions, the raising raises you up to the next energy eigenfunction. So basically, the energy eigenfunctions are separated by an energy of h bar omega. And a minus lowers you to the next state. All right, and so this gives you a super convenient way to find these states. If I can find, like say I can find one of the states, like say psi 2, okay, I can raise that to find psi 3, then find psi 4, so on and so forth, and I can also lower it to get to the lower one. So once we find one of the energy eigenfunctions, we're all set. And so the trick we're going to do this is we use this idea that, well, there must be a bottom rung. And I'm going to call that bottom rung psi 0. Okay, that's the bottom energy eigenfunction. That's the lowest energy. All right. By definition, there should be a lowest energy for us, and so we're going to assume that the lowering operator times the lowest energy function gives me 0. Okay, it must give me 0. And so if I write that out, the lowering operator, again over here, the lowering operator is this constant, and then since the lowering one, you'd pick the positive sign here, and so I'm saying that times psi 0 equals 0. So I can just get rid of the constant right away because it equals 0, and then write out my expression for p, and I get an equation kind of like this. And so this is a differential equation, right? It's an equation involving a derivative and a function. And again, if you know the tricks, you can go through and solve it, but we won't actually be doing that here. But if you go through and solve this, you get that the ground state of this looks like this, psi naught. Okay, so we call it psi naught. So that's one thing. The ground state is now psi sub 0, where before it was psi sub 1. This is just the way that it sort of works for these. And the one thing here is that we actually went through and normalized it to find it here. And so from this solution, you would have gotten that psi 0 of something like a times e to the negative m omega 2 h bar x squared, and then we use the integral of psi squared to actually normalize it. But once we have this one, again, by raising and lowering, we can find all the next states. And so that's what we've done here, basically. Okay, so now once we have this ground state here, okay, we can go through and figure out any of the other ones. And it's just a matter of sort of attacking it with enough raising operators to bring it to the next level. Now in practice, this is a big pain, but in theory we can do it. And luckily people have done it for us, so we don't have to do it. And you can find a list of these solutions in the book. Now, since we know the ground state, all right, what we can do is just go through and take this h psi 0, and if we do that, you can try this yourself, you come out with an energy of 1/2 h bar omega psi 0. So the energy of the ground state, we'll call it E0, is 1/2 h bar omega. And now the thing is, we know from our equations before, the raising and lowering, that basically we add an h bar omega each time. And so you can generalize the energy for each state. So like for instance, the state for E1 would be 1/2 h bar omega plus h bar omega. So you get 3/2 h bar omega. And this is the equation that generalizes to. And so here you've got these sort of shorthands. If I raise my state, I get this radical n plus 1 times the next highest state. If I lower my state, I get radical n, whatever that n you're starting with, times the next lowest state. So that's some things to sort of be handy with. And then next time we'll talk more about these, but the raising and lowering operators are in terms of x and p. You can actually solve the raising and lowering operators, or you can solve x and p in terms of the raising and lowering operators, and we'll see that that can be super helpful with different kinds of calculations. All right, and just real quick to end, here's sort of a summary of what we can get out of this. Again, if you look up, that ground state wave function, it's over here. Essentially, it's the Gaussian wave function. It looks something kind of like this. So again, this is what our potential energy looks like. If you looked at the potential energy graph, V of x, and these little dotted lines are the classical turning points for our certain energy. So these states are going to work very similarly to the ones in infinite square world. They're orthogonal with each other. Okay, here we start with 1 node, 2 nodes, 3 nodes, 4 nodes, etc. It's the same sort of idea. Over here we have the probability density, so the psi squareds graphed for the first 4 couple. The book will actually write out a few of these, and we'll talk about this more in class. And then just again, one thing that's interesting about the harmonic oscillator is that the difference between energies is equal. It's an amount h bar omega. That was not true for the infinite square well. Okay, so we'll talk much more about this in class.